Welcome. Let's move on to our second video in vector addition by components. Let's talk just a little bit more about reference angles. Please remember that in quadrant 1, your standard angle, theta, is equal to the reference angle, theta, or theta sub reference. Here is your standard angle in quadrant 1. In quadrant 2, it's a little bit different because your standard angle is this angle. And in this quadrant, your standard angle is going to equal 180 because you're not going all the way back down around to the x-axis, but it's going to be 180 degrees minus your reference angle. Let me get rid of that right there. Okay. 180 minus your reference angle. You may notice that this bow tie is lopsided. That's because it doesn't matter what your reference angle is. These standard angles will still be calculated using the formulas I'm writing. In quadrant 3, this would be your standard angle. So in quadrant 3, theta will equal 180 degrees plus theta sub reference. 180 degrees plus your reference angle. Notice we are always looking at how the reference angle relates to the x-axis. In fact, over in quadrant 1, we could have written theta equals 0 degrees plus the reference angle. Okay, we usually don't bother with that. We usually just remember that in the first quadrant, your standard angle and your reference angle are the same measurement. Okay, finally, in quadrant 4, let me draw this closer to the origin. Okay, in quadrant 4, your standard angle is equal to 360 degrees minus your reference angle. Okay, so review of reference angles. Do you have to memorize those formulas I just put up there? No, as long as you understand them and can interpret standard angles and reference angles from a graph. But what happens if the vectors are not parallel? Let's look at vectors A and B, drawn as they are here. And I have drawn, but not yet labeled, my horizontal component of A, my vertical component of A, my horizontal component of B, and my vertical component of B. Okay, now they are all labeled. We can take those vectors, we can break them into their horizontal components. Now what would happen if we added these things? Well, first off, because I can do this easily on here, let's see what happens if we add these vectors using tail to tip method. Our resultant vector should be here. I'll call that R. But we really could have done that same thing on the coordinate plane itself, right? If I had just moved vector B up here, or I could have moved vector A down to the other position, but I'm going to be consistent. It would turn out that the resultant vector is still the same. Okay, let's take a look at something else though, because this whiteboard can get a little finicky sometimes. I've moved these over here. So let's take a look at what would happen if we took the x component of A. Let's move it over here so it's a little bit easier to see. Maybe a little easier. Let's take the x component of B, B sub x, and place it, once again, tail to tip. Okay? And now let's add the y components. So here I'm taking my y component of A, I'm laying the tail of this vector to the tip of the one I just laid down. And now I'm going to take the y component of b sub y, and put it on the tip here. And hopefully this works out. It should. That this vector is, I'm a little bit off, but good enough for horseshoes. When you're doing it with algebraic methods and trigonometric methods, it will turn out to be exact. So you can add the x components, you can add the y components of the two vectors you want, and your resultant vector will be exactly the same as if you added the vectors themselves. So that's why we're doing vector addition by components. So let's look at an example. Let's add these vectors. Vector f, which has a magnitude of 154 and a standard angle of 90 degrees, 90.0 degrees, and vector t, which has a magnitude of 128 and a theta, or a standard angle, of 43.0 degrees. I will draw f in red, and y in blue. So at about 43 degrees, something about like that. Okay. If I add tip to tail, or if I do parallelogram method, I will wind up with the same thing. Let me illustrate that. So it does not matter whether I draw the parallelogram or whether I simply move this vector over here to do tail to tip. I get the same resultant vector. So either method is working, but let's do this by vector addition using components. Let's take a look at vector f first. Okay, it has a magnitude of 154 degrees and an angle of 90 degrees. Let's break that up. When you are doing these problems, I highly recommend you draw this chart. Make a row for each of your vectors that you're adding. There can be more than two. We're going to start with two. And make columns for your x components and your y components. All right? And let's take a look at the f of x, f sub x. Wait a minute, where is f sub x? For that vector that is moving vertically, there is no x component. That entire 154, whatever units it is in the y direction. So f sub y is equal to 154. Okay. The t vector is a little more interesting and complicated. To find the x and y components of these, and actually I added something to this chart that I do not need. I do not need this f sub x because I've indicated that that is f sub x by my row and column labels. So let's get rid of this f sub y also. It's unnecessary and it just clutters everything up. So let's now calculate the x component of our vector t. The x component of our vector t would be calculated this way. I'm just going to write this out to the side for the moment. I'm going to take the magnitude of t and multiply it by the cosine of the standard angle of t. And I don't need to write that in. That is indicated by its position in the chart. So I just write in here 128 cosine of 43 degrees. All right, then I need to find t sub y for this same vector. And we know that the formula for t sub y is the magnitude of t times the sine of the standard angle of t. And I will write that in here. Oops, and be careful. I often make that mistake. I start copying, and I confuse the sine and the cosine. So make sure you're using sine for the y component and cosine for the x component. Because you have such a powerful calculator, you do not need to evaluate those at that point. These are going to be an addition. Okay? So in your calculator, you can just put in 0 plus 128 cosine 43, making sure you're in degrees. And when you use your calculator, you will be finding x and y components of the resultant vector r. In this case, put in your calculator, check significant digits, 3 significant digits, and everything we were originally given. So we're going to express the x component of vector r as 93.6. If you add the y components in your calculator, you should get 241 when you round it. Okay? If you are asked to give the values for the x component of vector r and the y component of vector r, do so and round at that point. However, we're not done yet. And if you use the values we just wrote down here in the succeeding calculations, you're going to have pretty significant rounding error by the time you're done. So I recommend something else. Okay, I'm going to show you with these values, and I'm going to tell you how I'd like for you to do it. I'm going to go up to my original Cartesian axis here, and I'm just going to kind of erase this a little bit so you can still see what's there, what we originally had for those values. Okay, just get rid of some of it, because I want to concentrate on the resultant vector now. And what we have with this resultant vector is we now have its x component. Okay, here's my r magnitude. Here's my x component of r. Here's my y component of r. Okay, we know what the x component and the y component are. They are in the chart. But we do not know what the magnitude of r is. So if we find the magnitude of r using our Pythagorean theorem, and these values, we're going to take r sub x squared plus r sub y squared. And that is what we're going to do, whether we use our rounded values or not. So let's first use the rounded values. 93.6 squared plus 241 squared. Why am I putting it in parentheses when it's not strictly necessary? What would have happened if there had been a negative on one of these? Okay, we would have had to bring the negative into the parentheses. There is not a negative there, so we don't do it. But the parentheses help me remember to do it in case I have one. Okay, if I evaluate this, the value I'm going to get is 258.8186, okay, which rounds to 259, rounding to 3 significant digits. So r equals, I don't know where I'm going to write that, 259. But now we need to find theta, and we're kind of running out of room. Let's see if we can shrink this a little bit. There we go. Here's the formula we're going to use. I'm going to do this work in green. What we're going to do is theta reference equals the inverse tangent of the absolute value of r sub y, which is, in this case, 241, divided by r sub x, which is 93.6. When you do that inverse tangent, you'll get 68.795, which we will round to 68.8, and we are working in degrees. So our final answer for the resultant vector of the addition of vector f and vector t is r such that r equals 259, and the standard angle is 68.8 degrees. We have a magnitude, we have a direction from the x-axis counterclockwise. We're done. We found our vector. I'm going to post this real quick. Hopefully you'll be able to view it before class, and I will see you in Blackboard Collaborate.